Hello, everyone. Today, I'm very happy to have the opportunity to share our work at ICASSP industry expert talk. I'm Tao Liu from Tao Education Group, and my talk today is a practical guide to robust multimodal machine learning and its application in education. I have been working in the edtech field in the past few years, and currently I'm the head of engineering of Cheers 111 at Tao. And my research area lies in all aspects of AI in K-12 education. Our experience of the world is multimodal. We see objects, hear sounds, feel the texture, smell odors, and taste flavors, and then come up to a decision. Multimodal learning suggests that when a number of our senses are being engaged in the processing of information, we understand and remember more. By combining these modes, learners can combine information from different sources. Especially in my talk, I will focus on learning from multiple modalities, including language, image, and sounds. When it comes to the topic of machine learning or deep learning, a large body of research works are dealing with learning data representations. The effective representation can solve the majority of industrial ML problems as well. So in my talk, I would like to share some of our latest experience about bringing together information from different modalities and achieve better and more effective data representations. So here is the outline of my talk. In the first part, I will talk about our work of multimodal learning for audio and language representation. In the second part, I will share some practical research efforts about robust language learning. Third, I would like to show you some research-driven product we built and then conclude my talk. So the first part, multimodal learning for audio and language representations. As we all know, there are tons of rich information contained in both language and voice. The language focuses more on the content, and the voices contains extra emotion and feelings. Information from both modalities are very useful when building practical machine learning applications. Let's take speech emotion recognition as an example. The speech emotion recognition task is given an audio clip of spoken sentence, decide what emotion it is. The traditional approach to handle such multimodal tasks usually falls into the late fusion paradigm. As you can see here, we first get the transcription from the audio signal. Then we extract the sentence level embeddings from both the linguistic and acoustic information respectively. Once we get these embeddings, we directly apply a fusion technique, for example, concact, to get the fused representation and use it for the emotion prediction. The above approach is simple and effective. However, we would like to make it better. At all, we don't want to unconsciously concact the sentence level embeddings from two modalities. We come up with an idea of conducting fine-grained multimodal learning. Specifically, we first conduct the temporal alignment, which, as you can see here, we align the pronunciation of each word in the audio stream. We use existing alignment tools to get the start and the end timestamp of each word in the audio signal, and we apply min and max pooling to extract the word level embedding from the audio signal. After such temporal alignment min-max pooling operation, we get the same number of word embeddings from both modalities. Once we have the initial embeddings from both audio signals and the transcriptions, we conduct the embedding fusion by cross-modality excitement. So the excitement is a trick from computer vision, if I remember correctly. Basically, it works like this. From the view of the language, it finds which part of the voice is important, and from the view of the speech, it finds which part of the language is important. Specifically, we use the sigmoid function as the excitement function, and we use the embeddings from one modality to compute the excitement weights of the embeddings of the other modality. In such a way, embeddings from one modality are weighted by the importance from the view of the other modality. So here is the overall framework of our proposed approach. which consists of four important blocks. From the bottom to the top, the first component is acoustic and semantic encoders, and then we do the alignment to align the frame level acoustic information with token level embeddings. Then we do the cross-modality segment, and at the end we extract the information from the fields embeddings. We validate our approach by two commonly used datasets: the MOCAP and the red DES. The datasets are the standard test set for speech emotion recognition. The results here demonstrate that our approach is superior on the prediction task for multimodal speech sentence, and it outperformed a wide range of baseline in terms of prediction accuracy. Furthermore, we conduct detailed ablation studies to show that our temporal alignment min-max pooling mechanism and the cross-modality segment significantly contributes to the promising result, as you can see from the table here. Meanwhile, in order to encourage the research reproducibility, we have open sourced our code at the following address here. Okay, so in previous work, I briefly talked about the directly learning embedding fusions from two modalities. However, there are lots of works going on beyond that. Nowadays, pre-training becomes a buzzword and it's prevalent across many research areas. Here is a graph showing the standard ML workflow with pre-training. Typically, a large-scale model is pre-trained on some unlabeled data, such as bird. Then for conducting predictions for specific tasks, we conduct fine-tuning with a task-specific dataset, and the objective is optimized with the task-specific loss. BERT is probably the most popular pre-trained language model. Here is a picture I grabbed from the internet, and you can see here, since BERT was invented in 2018, many improved versions are developed. As you can tell from the model names themselves, lots of existing researchers focus on combining both visual and language information. Little has been done for utilizing information from audio and language modalities. Here, I would like to introduce a pre-training cross-model transformer we developed at all for building practical ML solutions in education scenarios. Here is the overall model architecture of our proposed approach. Our cross-model transformer is built upon the standard encoder-decoder transformer architecture. The left part is the standard transformers encoder part, and we don't change it at all. We made several modifications on the decoder part, which is the right part. In our approach, the key component is the multi-head cross-model attention, which builds the intrinsic connection between language embedding and acoustic embedding. As you can see from equation here, we use the language embedding as key and the value, and we use the acoustic embedding as a query in the standard attention formulation. In such a way, we are using the learned language representation to represent the acoustic information. In the loss part, we combine the standard masked language modeling loss and the masked cross-model acoustic modeling loss, which use the weighted language representation to recover the masked acoustic information. With these two loss functions, we do the pre-training for the audio and the language unlabeled data. Once we have the pre-training models, we want to use it for fine-tuning, we apply the standard cross-entropy loss. Meanwhile, in order to capture information from different modalities, we design an orthogonal regularization. So as you can see here, the orthogonal regularization will prefer the representation learned from the two modalities dissimilar. We conduct the pre-training with two sets of parameters. As you can see here, this gives us two model variants, a base one and a larger one. Our CTEL model is evaluated on 3 well-studied tasks, including emotion classification, sentiment analysis, and speaker verification. And all the relevant results are listed here. And apparently, our model has the best performance. And also, furthermore, we conduct detailed component analysis to well understand the proposed model. And due to the time limit, please check the details in our EMNLP paper. Okay, so this is the first part, and in the second part, I would like to talk about the robust language learning with noises. As we all know, from the view of industrial companies, building practical ML solutions is always in the very noisy environment. So here I will show you some examples in the educational scenarios. Here, as you can see, when building the auto mental math grading and searching applications, we have to handle a lot of handwritings from the kids. And we all know those kind of handwriting are very hard to recognize. And also for a lot of math tutor apps, we have to handle such handwritings and we have to recognize them. See, so there are a lot of very cool applications built from Photomath, Microsoft, and Pearson. Okay, and also another example is the auto essay grading. I believe everyone is quite familiar with Grammarly, which is auto essay grading tools for student essays. As you can see, the video here I grabbed from the Grammarly website is the AI programs will kind of find the misspelled words and it will evaluate your about the relevance, correctness, clarification, and all the stuff. So the problem is when the NLP meets the OCR, it's very difficult, right? So I also took a picture from the internet. So on the left is a kind of a handwriting from a kid, and on the right is the OCR. Is a transcription is a transcribed result from the OCR engine built by Amazon. As you can see here, the recognized word is very horrible. So this kind of recognition errors bring huge challenges for the downstream NLP models. So in the literature, there are a lot of existing approaches try to handle such things. So this can be divided into two approaches. The first part is do the pre-processing modules for the noisy reduction. For example, we can run spell checkers. We can run advanced spell checkers. People in the NLP community, they call the grammar error correction, which is GEC. And also nowadays, people can utilize the kind of super large language models to kind of do the corrections. And the second approach is we can reduce this problem by data augmentations. And we can, nowadays, the adversarial training is kind of popular, and we can do the white box attack and the black box attack to generate adversarial samples. However, so the existing approaches, they kind of, when they do the noisy reduction or adversarial training, they don't consider the OCR error distributions, which is very important in the educational scenarios. So all these existing approaches cannot handle the OCR errors. So here I give an example here. So there are kind of two types of OCR errors. The first one is the character level errors. As you can see here, when we use the OCR service, some characters may make misgenerated, right? And also, because the OCR have to infer the kind of infer the meaning of the entire recognized sentence. So sometimes they have the span level errors. I show you a very funny Chinese recognition result, and also the translation, as you can see here, is totally different. So based on these intuitions, so we in our work we developed a multi-source OCR noisy simulation, which kind of focus on how to generate the noise, the noise, the how to generate the synthetic noises, really based on the OCR distribution, OCR error distributions. Our simulation have three components. The first component is the Ruby simulation, kind of focus on the token and the character level errors. And also we use the attack-based simulations. It still is focused on token and the character level errors. The attack-based simulation is just replace tokens with its synonyms at the weak spot. The weak spot is using the standard. We find the weak spot by checking the gradient. And in the model-based simulations, we want to kind of focus on the span level errors. So we kind of train the transformer models on the parallel data of the human transcription, which is kind of the ground truth, and the OCR transcriptions. We use the transformer to generate the span level errors. And to make it work, so we also add two very effective heuristics. The first one is hard example mining. So at each iterations, we use the current model to compute the representations of the noisy free samples and use it to simulate the noise band. And then we select sample pairs with the largest cosine distance. And also we use the stability loss, which kind of minimize the disagreement between the model output and the clean input. So here is the overall framework. So in the bottom part, we have three components to generate the noises based on OCR simulation, and then we select hard examples, and then we add stability loss in the final optimizations. And also we did the experiment on three data sets in the educational scenarios, and we also tried the two OCR engines with different recognition error rate. And here this is this is the full result. And as you can see here, our approach almost achieves the kind of the best performance under different OCR engines. And also we try ablation studies to check the impact of our hard example mining component and the stability loss component. And you can see here, these two heuristic kind of boost the performance quite a bit. And at the end, we check what is the impact of different noisy levels, and we simulate the noise from the 5% to the 40%. And as you can see here, if the noise is kind of under 10%, our model is pretty robust. And with the increase of different noise levels, the performance kind of dropped a bit. So this is just one simple example when building ML solutions in educational scenarios. So the real world noises are way more than the OCR errors. I will show you another example, which is called a Cambridge sentence. As you can see here, I just show you an example of Cambridge sentence. People can read every word in the sentence and understand the meaning of sentence. For example, here, according to a research at Cambridge universities, it doesn't matter in what order the letters in a word are, right? I don't read the whole sentence, but as you can see here, I can read the sentence with no difficulties. However, if we pay detailed attention here, every word in the sentence is spelled wrong, right? So the letters are not in the correct order. So this kind of sentence is called the Cambridge sentence. So if we put those kind of sentences into the Google translations, it breaks, right? So we cannot get the correct translations. So we kind of build the NLP models trying to kind of do the correction in the Cambridge sentence settings, right? Basically, we developed a model trying to capture, similar to the previous work, we're trying to capture both the character level sequential dependence and the word level sequential dependence. So here we developed a model called the MOOT, which is a framework for the robot word recognition. And basically, the idea is very simple. We use kind of the transformer encoder to capture the character level dependence, and we use the LSTM to capture the word level dependence. And actually, it works quite well. To check detailed, please see our AAA paper. And in the third part, I would like to talk about I will give a brief overview about our multimodal ML applications in educational context. So as we all know, nowadays, we have offline classroom and online classroom, and they are merged together, and we don't distinguish those kind of different classrooms quite well. And here I will show you an example of the application we built called class activity detections. So here is the problem. So as you can see here, I took several pictures from the offline one-on-one classroom, and in this kind of classrooms, it's more like a black box. We don't know what happens in the classroom, right? We don't know what the teacher teach, and we don't know how student studies. So here we collect the voices from the classroom, and our task is we want to split the voices into 3 parts, and we want to know which part is the teacher is talking and which part is student talking, which part is no voices or noises, right? So this in the educational scenario, this task is called class activity detections. So the first solution we think of is okay. So it's kind of simple because we know the teacher, right? We can collect the voice samples from the teachers, and we can extract the voice biometrics from teachers, and we just do the matchings. So yeah, it works. And so we build a kind of we build a solution with the voice biometrics in the class activity detection task, and it works. The pipeline is kind of straightforward. We extract the voice biometrics and use that to do the matching from the classroom recordings. And but later we would like to think about a solution. How can we solve this problem without voice biometrics, right? So here, we come up with a solution called multimodal attention. So basically, the idea is pretty simple because it is a one-on-one classroom, and we only have one teacher and one student, right? So the kind of the spoken content from the teacher and student are quite different, right? They say different things. So what we do is, so basically, we use the acoustic informations as the query in the attention formulations, and we want to we first use the acoustic feature to do the kind of clustering stuff. We cluster all the segments into 2 parts, right? So but we don't know which part is student, which part is teacher, but we know because their voices are different, we can do the clustering, and they are split into 2 groups. And then we use the content. We use the content from each cluster to make classifications, because the spoken content from the teacher and student are quite different, and it's very easy for us to do the classifications. So basically, that's kind of the idea from our multimodal attention layers. And we implement this idea and show great results. So next, I will show another very cool application we built. It's called Spoken Language Proficiency Assessment. So here we want to encourage students, especially students in elementary school, to kind of practice their oral language skills. So here we developed a task called the verbal fluency task. The task is very simple. For example, here Let's say if we want to cut a loaf of bread into 20 pieces, how many cuts do we need? So in this kind of verbal fluency task, we don't really care about the answer that much. We kind of want students to think aloud. We want students to think about how they solve this problem, or what's their thinking behind the answer. So here I will show you an example. It is in Chinese, but you can get a feel of what we collect from the student.
我们来看这一题，这一题是切法式小面包，就是说，你看这个是切了10下，再加上原来没切的这一段加1，那就是11段。这一题是我一共有20段，请问我切了几下呢？是说我一共有20段。减去没切的这一小块，那就是减1，20减1等于19下，那就是我一共切了19下。
So as the example shows here, so we give the task to the student, and the student they are solving the problem in a think aloud way, and their parents took the video and their parents will upload the video to us, and we use the video to do the assessment. So this is the workflow, and here we build the auto assessment tools to given the student given the student videos, where our tools will analyze the student oral language skills in 6 dimensions. For example, the student's verbal fluency, the topic relevance, the coherency, and the emotions and the interactions, vocabulary diversity, and so on. So, and also they say we make it as a very cool tools, and for people understand Chinese, you can try our the WeChat mini program, or just visit that link, and you can just try the application we built. The other task we are trying to solve is we besides the grades we gave, right? Besides the grade we gave in the previous work, we also want to give comments to the student, right? The comments are constructive feedback, and the comments will help the student to improve, right? However, generate such feedback for teachers it's a lot of work, right? We would like to use the multimodal feedback generation techniques to generate the feedback from the videos automatically. So that's the task. And here we come up with a multimodal feedback generation framework, which extract information from text, audio, and images. And we have a modality gate to control which part of information is important, which part of the multimodality information is important for generating current word in the feedback. And the result shows a very promising result. And that's all the 3 parts in my talk. And I would like to conclude my talk and give a future outlook. So as we all know, the development and the application of AI is bringing rapid change to almost every aspect of our life. To prepare people for the change to their lives, so we must ensure that our education and training is tuned to the new demands of the workforce and the society. There are huge opportunities and challenges about applying the machine learning and the deep learning techniques into the educational context. So yeah, so this is all my talk, and here these are all the references I mentioned in my talk. And also in the past we have held a lot of tutorials and workshops. And if you are interested, please visit our website, ai4ed.cc, and here is all the previous workshop tutorials. Yeah. Okay. Thank you very much.